So I hope everyone can hear me even without the mic. But yeah, I'm Anu, and so I'm going to speak about this project of ours, which all the team members are listed here. More than half of them I haven't met in person yet, but that's going to change soon because Christo was my advisor at NWU in South Africa. That's where I just finished my postdoc, and I'm starting my next postdoc in the US with all these people. So finally, I can see them in person. So before I begin, I want to mention that not I don't think anyone here works specifically on neutron stars, but the way I have put things together, there are some details, and some of them like you can always take away some parts of this talk because there will be something about theoretical modeling, something about data, something about simulations and MCMC. So there is, I hope there is like takeaway for each one of you, and maybe it will lead to some nice discussions. Um, just to mention, in last conference, I had very good discussions with people from solar physics because of the magnetic field similar topics. So I divided it in three parts mostly, where I'll try to answer why we are doing this, in which I'll give some introduction, and then how we are doing this, which will entail something about background and motivation, and the tools which we are using. And then I'll answer what we are exactly doing right now, which is basically our current work about the magnetic field and our approach, which has the details I was just mentioning. So why? Simple answer, equation of state. So equation of state, nuclear equation of state basically describes states of matter. So so the relation I have written here is for ideal gas, PV equals nRT. So this relation is analogous to mass radius relationship, right? Because you can always make correlation between the pressure, volume, temperature, and the size of an object. So that's the idea to understand the equation of state. Now, this is basically just a cartoon. So when we plot equation of state, these three different lines are representing three different models, where some have like the maximum mass over here. Another model predicts that the maximum mass could be a bit higher. So this multi-valued, right? Yeah. So I'll show one which has actual real models because this is just cartoon. So let's go to that slide and then we can come back to this. So yeah, so neutron stars, when an intermediate mass star is basically running out of its fuel, and there's supernova, so it's what's left over at the center, at the core. So, and these are extremely compact objects. So their density could be like several times that of nuclear saturation density. So which makes them perfect non-terrestrial laboratories, as these are called, to understand how matter could be behaving at such extreme pressures and densities. So coming back to the cartoon, so this is again, these aren't very precise. In the next slide, I'll show the actual real models. But just for an idea, the thing in which these different equation of state models are varying is basically the internal composition. I was trying to move it there, but okay. Basically, the internal composition of the neutron stars. So, like the first one could say that, okay, it's composed entirely of quarks, and then the second one, sorry, yes, the second one could have a different configuration. And now coming to the real after this. So what we want to do is we basically want to estimate mass and radius of neutron stars, put a dot here, and then say, okay, this is the equation of state model, which best describes our observation. Now coming to the real plot. So I have radius in kilometers and mass in solar masses over here. So yeah, you did mention the multi-valued stuff, and yeah, okay, they disappeared now, which is fine because I don't know the answer anyway. But I'm just gonna say, oh yeah, that's pretty good. So yeah, but I wanted to show the animation after, but I already skipped that. So anyway, so I honestly don't know what the short forms represent because my part is to put the estimates of mass and radius on this plot. And then it's the job of my equation of state studying colleagues to figure out which model is fitting the best. So I don't have the details about this, which at least for this particular presentation, it's not too relevant anyway. So just for an animation, just an animation showing what we are doing. So I started with 26 models in this slide. And what we do is we put observation of a pulsar over here, this horizontal line. And based on what the mass of it is, we can already rule out the equation of state models, which have maximum mass prediction lower than that. So we started from 26 models, and with three estimates, we have 9 models left in the end. And imagine when we have lots of neutron star mass and radius estimates there, with good precision, we can make much better constraints on which model is actually going to work in the end. So just summarizing the why part of it, it's to understand the equation of state, to have insight into the extreme properties of matter. And for that, we need to calculate mass and radius of neutron star, which is where NICER comes in. So NICER stands for this, Neutron Star Interior Composition Explorer. So it was installed aboard International Space Station in 2017. So this white box over here is NICER. And these small hexagons, I think, they are 56 X-ray photon detectors. And in the background, you can see the wing of the International Space Station as the station is rotating. So it's kind of small compared to the size of the station, of course. So what these photon detectors do is they measure the energy and time of arrival of photons, and it operates in soft X-ray band, so 0.2 to approximately 12 keV. And what makes it very such a nicer object, is because of its exceptional sensitivity. And just to put some numbers, maybe some of you are using something from, I don't know, maybe XM Newton or something. So this is just a comparison that is 4 times better sensitivity than what XM Newton have. So, and one of the science goals, as you can guess from the name itself, is to explore the interior composition and hence constrain the equation of state for neutron stars. So, and then it observes millisecond pulsars apart from other objects, of course. So millisecond pulsars are old neutron stars, which have recycled, and their period is approximately less than 30 milliseconds. Now, why millisecond pulsars? First, because like normal pulsars, they have stable rotation rate. They have stable rotation rate, which ensures precise measurements coming to their light curve and the size estimate of the star. And second thing is because of gravitational light bending. So I'm going to show this another animation. So this is a low mass star. As you're increasing the mass, you can see that you start seeing basically the other side of the object, right? Because of the gravitational light bending. And in terms of millisecond pulsar, this basically means that, so these orange blobs over here are what we call as hotspots. So they are the emission sites. So what's happening over here is for a low mass star on the left, you see them once per cycle if there are 2 spots. But for a heavy mass star, like a millisecond pulsar, you see them throughout the cycle. So we are basically using gravitational light bending to see what the geometry of the emission region looks like. So what we have is the thermal X-ray light curve of millisecond pulsar. So light curve basically, so I have it over full phase, 0 to 1, 0 to 360 degrees, and on y-axis it's photon counts. So the idea for millisecond pulsar is that the thermal X-ray light curve is confined to the surface of the millisecond pulsar. So what we do in the end is just predict where on the surface of the millisecond pulsar this light curve is reproduced from, because it's X-ray and because it's on the surface. Well, I mean, it's basically a model, right? So, but I mean, for hotspots, like it's basically like what sun has, right? So it has sunspots with different temperature. Yeah, exactly. Yeah, So the particular pulsar I'm going to talk about is actually isolated. And I agree that they are different, mechanism is different, but the idea was that you can judge them based on different temperatures. So when I'm making a surface emission map for sun or millisecond pulsar, by temperature wise, you can say, okay, well, I mean, for millisecond pulsars, we think it's from the surface emission. So there are atmosphere models, which emission line region it might be from. And atmosphere model is something which is going to be a follow-up work of our project. I'll speak a little bit about it afterwards. So yeah, this is my the source we are studying, PSR Pulsar J0030+0451. So it's an isolated millisecond pulsar, and its spin period is around 5 milliseconds. And yeah, the light curve I was showing is for J0030. And you can see two peaks in one rotation phase. And as I said, the possible origin is the hotspots, the emission sites on the surface. And again, just to reiterate, and so you understand me perfectly fine, we want to model the hotspots and constrain the neutron star equation of state. So nicer team, so there is a statistician team sitting there at NASA. So they used this Bayesian inference approach. What they did was they took the light curve of J0030 and they assumed some shapes of the emission spots. And in the end, after a whole big statistical magic thing they did, so these the two rows I'm showing are two of their good solutions. A and B differ only in the where we are looking at. So this is the front view and this is the top view. And same for the second solution. And on the right side, I put the radius and mass estimates, which they estimated in the end. Now, depending on what field you work, these error bars are either small or big to you because it depends on what data or what source you're working with. But for neutron stars, these are revolutionary numbers because such precise measurements to order of first, second decimal place that has never been achieved before. And that was the aim of NISA. Now, you'll also notice that the hotspots in the two solutions, they are either 2 or 3 in number, and they are oval and arc shaped. None of them are spherically symmetric or symmetric with respect to the hemisphere. And they are in same hemisphere, like in the southern one, which means that the only field configuration which can describe it is the non-standard, non-dipolar magnetic field. So far in neutron star literature, that's a line of sight. So they just put that for reference. So, I said this, that it has to be a non-dipolar magnetic field. And I see some people are nodding, which is great. But I still want to illustrate why exactly I made that statement. So here is an illustration. So I put my neutron star over here in the center, the white sphere. And this red is my rotation axis. And yellow is basically magnetic moment. And the blue lines you see are dipolar magnetic field lines. Now, here is my overly exaggerated north and south pole, basically, for dipolar field. And if you want to plot them on the so-called Molbeat projection, which is where we plot our world map, this is what they're going to look like. So there is absolutely no way that you can have a dipolar field and have hotspots in the same hemisphere. That's what the case for non-dipolar field is. So it has to be a non-dipolar magnetic field, and I hope everyone is nodding now. Well, I mean, so what NICER team did was statistically based, and I'm just going to mention what the cons about that approach are. And what we are doing is something physical, magnetic field. So, I mean, in the end, so physical answer is all my talk is about. But just to, I mean, just to put things in perspective, in the end, it's model. It's not like I'm seeing a pulsar map and I can see the hotspots because it's too far away for us to do that right now. So we have the light curve, and let's see what all we can do from that. And that's what we are doing. And just to mention this Bayesian inference approach, so they actually independently worked on this at the same time, and they had almost similar results in terms of the estimates. So, and they also published the whole open code and everything. So, yeah, it's I forget the affiliation, but I think it's an old guy. Yeah, yeah, yeah. Cole Miller. I don't know if you're talking about same thing. Maybe there are too many old Millers in the field. Sorry. But yeah, they did it independently, and other groups have reproduced the result using their the approach they mentioned, and they have gotten to the similar conclusions. So it's very robust. The problem with this is, I'll show here. So one, again, it's non-physical approach. It's statistical, starts from assumption, and just gives us the shape. It's great, but it's also computationally heavy because they have to run through so many combinations to get what we just saw on the previous screen. But what happened from this analysis results was, so yeah, just to conclude, so an isoteam analysis, and we got precise mass and radius values already, but they're non-physical and they're computationally heavy. But because they gave us some idea about the hotspots, we know that it can't be a known dipolar. We know that it has to be a known dipolar magnetic field. So this all led a motivation for us to begin modeling the multipolar magnetic field, which is something physical. So this is hopefully this makes more sense by the time project is finished. So coming to the multipolar magnetic field part. That's true. That's absolutely true. But if you dig up the neutron star literature starting from, yeah, yeah, it's easy to handle. Exactly. And I know multipolar isn't easy to handle. It took me months to get to the final equations. Some literature, some papers, even from 70s, 80s, they did explore that, okay, it has to be something beyond dipolar. But because, as you just said, because it's so easy to just implement a center dipolar field, everyone has been taking that. And now we have such sophisticated instruments where we can see, okay, this magnetic field configuration can't explain this data. So it's time we move on to, something a bit more realistic. So it's not surprising, I agree. So yeah, in 2021, Kalabutarakos et al., they did begin this project already, and they published it in 2021. So what they did was, I'm going to make another column in next slide where I'll show the differences between this work and our current work. So just to highlight, they went up to quadrupole component, dipole plus quadrupole, and they also made a very simplified assumption about their subcomponents. So M is total number of components is 2L plus 1 minus L to L, but they only considered the one which is aligned with the rotation axis. And they considered a static star, which means pulsar is actually not rotating. So your field is very symmetric and not realistic at all, but it's a good start to go with. And then they also considered an offset field. I'm going to use this term afterwards. So I just want to explain what it means after I drink some water. So if this is my pulsar and that's my rotation axis, this is my magnetic moment, right? So the center of the star, the center of the rotation axis, and the center of my magnetic moment, they all are coinciding, right? That's what a dipolar field geometry we have been raised up with. What an offset field means is my magnetic moment has moved away from the geometrical center of the star. Now, there is whole uh, physical reasoning behind it that maybe pulsar received a kick during the birth, during supernova explosion, and that's why the magnetic moment is a bit away. It makes it a realistic scenario, and that's why many works do consider an offset field. But what we wanted to do was start with a centered field, invoke as many subcomponents as you can, and I'll explain why in my next few slides. So what we are doing now is, for beginning, we are going up to L3 component. So we have one extra component, and we have all these subcomponents. So there are no assumptions about limiting them. And it's a retarded field. So now my star is rotating. My field lines are rotating, which is what actually happens. So it's more realistic. And I put offset later as a question mark because we start with centered. And if we find out that maybe for this source or for next source, centered field is not working out, we can put an offset in our field. So that can be done. But we want to see what happens with centered. And let's see. Yeah, but just for summary. Yeah. Yes, exactly. In after a few slides, I'm going to show what exactly the difference looks like. But yeah, so there are no assumptions about subcomponents, and it's a complete description, by which I mean, if any of you ask me to invoke I don't know, 112th component, it can be done because it's an infinite series. We probably don't need to go that far, but it's possible. And yeah, centered field. So this is what the expression is. There is a radial component, polar, and an azimuth component. And as I said, L goes from 1 to infinity, and M goes from, for each L, it goes from minus L to L. So it's dipole, quadrupole, and octupole. And after working out lots of equations on paper and paying, I don't know, many dollars to Mathematica, this is the simplified version we reached, which as you can see, it can easily be implemented in a code. These are analytical expressions. So, but now they are working efficiently. So we started with a code runtime of very high because analytical expressions, and then were cos theta, sin theta, all these calculations. But right now it's working very efficiently because of the simplification. And just to highlight or break it down, so these components are with radial dependence. So f is actually a function which is directly proportional to spherical Hankel functions. So these are just some functions which decay exponentially with radial distance. And then there is theta and phi dependence. And y here represents, from quantum mechanics, you might remember, spherical harmonic functions. And rest everything is just constants depending on L and M. So yeah, that's what I meant by the details. So I'm going to speak about the little ingredients which goes in our methods. So hopefully each one of you will have some takeaway or something to discuss after that. So we have a Markov chain Monte Carlo implemented. And for starters, spoiler alert, our mass and radius for this project is fixed right now. We are borrowing the values from previous results because the idea is to implement this complete magnetic field first, have parameters for that field, and in the second part of the project, free our mass and radius. And in that case, our photon trajectories will be calculated at each step because that depends on the mass and the radius of the neutron star. So for now, this is something like a ready-made ingredient we take from literature. And then we put in the module for our retarded field, which I just showed in the slide before. And just for you to get a sense of what the parameter space looks like, I wanted to introduce these different parameters I have in the field. So here is my neutron star and XYZ Cartesian coordinates. So for dipole, it's showing the dipole magnetic moment in mu d. So you need basically two angles to describe its symmetry, one for the orientation and one for the phase. So I have two parameters so far. When I have L2, it becomes two dipole moment and one phase. So it's 3 now. And for quadrupole, it increases again. So in the end, I have a total of 3 phase, 6 angular, 9, and then 2 more parameters, making it a total of 11. The 2 additional parameters are field strength of higher components, which are normalized with respect to dipolar field strength. So it's a total of 11 parameter space now. And as I said, when we free our mass and radius and line of sight and different ones, exactly. I just start from like B, D as 1, and then we can convert it to real terms later on. That's not an issue. But if my BD is 1, what's my BQ is going to be? Let's say it's 4 times, it's 10 times, and that's the factor which becomes a parameter here. So yeah, I have 11 parameters, and when we free other parameters, it can go up to 14 or even more if we are putting in later on, like in next steps of the project when we have energy dependence and other things put in. So we move on to calibration because one of the most important things about analytical equations have been to determine the number of, not number, the precision they need. Do I need an 8-bit precision? Do I need a 16-bit precision? And we wanted to be sure of the exact number to save computational cost. So we started plotting magnetic field lines, of course. So here I show quickly for L1, 2, and 3. And you can see clearly as you are moving to higher components, the 1 by r to the power L plus 2 dependence. So close to the surface, octupole component does make contribution, like it can't be avoided. And this was like the final test for our precision. So this is a very special case of magnetic field lines. So when this was my rotation axis, if my magnetic moment is at 90 degrees to it, that's what we call an equatorial case. And in that case, my field line is going to start from here. Yes, exactly. And it's never going to rise to the Z axis. It's going to stay confined to XY plane if my precision is good enough. And we started with something which wasn't good enough, and then it was like making weird shapes. So this is how we concluded that, okay, now we get the 2 spiral arms for dipole. This is good enough precision. Let's go ahead and do it for quadrupole and octupole. And you see the spiral arms for all different components, which is a feature of these equatorial field lines. And that's so. Yeah, so RLC is something I can work it out on paper, but yeah, so this red circle is basically representing the closed magnetosphere of pulsar. So the pulsar is the very small dot at the center, which let's say is 10 kilometers, and then you can scale from there that it goes beyond. But well, yeah, I mean, 10 power, I think it's higher than 10 power 12 gauss, which is for, I think, for normal pulsars. For MSPs, it's, no, it's lower. So, yeah, 10 power 12. But I mean, not as high as normal pulsars, but definitely you're right. And and this is the first object we are studying, and it's relatively easy to do it for an isolated pulsar. Our next target is accreting, so we'll have to think about all these things when we turn to that object. Okay, so yeah, this is what determined our precision. And then, yeah, that's the magnetic field lines for static and retarded I was mentioning about. Now, if you just look at the red field lines, you see that they are symmetric in both right and left, which is what you will have for a static star. My field line is starting from here, going there, coming back. Same for this thing, 180 degrees difference. But when you have a retarded field, my field line is going to start from here, from my head, and then it's going there. Now, because my it's so far away from the star, and the speed of a particle, for instance, which will be traveling along the field line, close to the surface, it's going to be different than what it is at a faraway distance, right? And that's what defines this twisted shape. And that's what we mean a retarded field line, which it's exactly, yeah. So static is again something like a center dipole, which people assume, yeah, yeah. Yes. So even for retarded, we can take a snapshot, but at least it's a realistic snapshot because it's showing the twist, which is real. Okay. Okay, so that's the difference between static and retarded field. And next, so we have 2 ingredients ready now. Next, we move on to polar caps calculation. So I'm using these terms hotspots, emission sites, polar caps a bit interchangeably. So I hope it's not very confusing about that. But next step is to calculate where the polar caps are. And then we calibrate, which is something like this. So just to mention, if you're interested in the very details, so this is basically a model showing how you can calculate a polar cap. So that's the rotation axis, and this is showing for a dipole. So it's magnetic dipole axis. Now I start from theta 0 along the rotation axis, and I go up to theta 90, and I plot every single magnetic field line, different resolution. And then I keep checking which field line is making a closed loop. Now for closed loops, that's defining my magnetosphere. Now everything which is open, and if you just, everything which is open lies inside this shape. So yeah, the cone, exactly. So if I take it from a center, then it looks like a cone, yeah. So if I make locus of all the foot points of all the open field lines, then you get this orange shape on the surface, which is what my polar cap is. And the figure I showed in the beginning is calculated using this method, and you can see it on a mole bead projection. Now I show it for dipole here. It's this and this are same. It's just a different way of representing. I just haven't put these caps on this projection for plotting purposes yet. But for dipole, as expected, you see two caps, and depending on what your orientation angle is, of course, they change. So for 90 degrees, your pulsar is going like this, my north pole, my south pole, and for each phase of rotation, you see two caps, which is what's happening here. Then I plot it for L2, and I'm showing it for this selected number of cases. We tried it for many different orientations. And you can see up to 4 polar caps for quadrupole, as expected. So that's calibration going well so far. And then for L3, so sadly, I have the case here which only shows 6, but because it's an octupole, you can see up to 8 polar caps there. Now you will see that the caps here are these very thin lines. Now imagine if my resolution was not good enough. If I had missed this particular phi, I would miss the entire cap. So another point of doing all this calibration, apart from precision, avoiding typos, was to determine the resolution we need to actually see the emission spots. So that's what this determined. And just to mention, in literature, people have plotted polar caps up to L2. So this is the first time you're seeing this rainy plot for octapoles. There was something interesting and something which we actually couldn't calibrate with, but we can guess that from here going to here, it makes sense. Okay, when we have all the ingredients ready, field equation, calculation, our initial conditions, we start producing thermal X-ray light curve. And for each step of my MCMC, I compare my model light curve with nicer light curve. And that's how I keep calculating log likelihood. And in the end, I have minimized my log likelihood, and that's my best fit. Okay, I'll move to results. Sorry, I need to sip water again. But I don't know if you want to ask your question now or. Mm-hmm. Yeah, I mean, but in the end, it's escaping from an extra step, right? Instead of transformation, which actually you have a very good point. So what I can show you in the equation over here. Yeah. So this term you see nope. This term you see exponential I time phi minus n. That's basically doing exactly what you're saying, the transformation bits. And that's what making it retarded. So it's same thing worked out. So it's just that the idea has been put in from the very first, when we begin the equation that, okay, this is the solution for an outgoing spherical wave. Let's put retardation in. Then we don't worry about transformation later. Okay, preliminary results. It should have said that. This is the bestest of the bestest solution my MCMC found for a dipolar field, which is to be expected. It's nothing going wrong. It's going everything right. So, and I increased the number of steps, computation time, and everything just to make this final statement and agree with everyone else that standard center dipole is not enough to explain nicer data. And this is the solid proof for that thing, as solid as we can make it. Then I turn on my quadrupole component, and it's starting to make much more sense now. And here is the corresponding emission spots, which looks similar to what nicer analysis team has produced, different shapes, crescent, and in same hemisphere. And I just want to make this very small but important point here. There is no offset. This is centered field with all these subcomponents. That's what I was mentioning before. Maybe you don't need an offset. And I'll bring this point back again in the discussion after a few slides. Then I turn on my octupole component, L3. So this is dipole plus quadrupole plus octupole. Now, in quadrupole case, I managed to find only one solution for same number of runs and conditions computation time, which means that it was a bit more constraining or limited. But now, because I have more free parameters, octupole component, more subcomponents, I was able to find 4 unique solutions. And by unique, I mean in terms of these emission geometry. So I have different light curves, different parameters producing similar light curves, but they are of same family. And by family, I mean they look really same to this emission site here. So these 4 are unique solutions. So I'm not including the number of the families I determined. So this is what the final output from up to quadrupole is. Yes. Yeah, so every emission site is corresponding to this model light curve. So, I mean, each column is one particular solution. So by 4, I mean that there are 4 solutions which have acceptable reduced chi-square values I determined. Exactly. So this light curve, which actually looks, they all look pretty same. But that's, I mean, if we go in and I overplot all of them, then you see the very minor differences. But that's also because NICER has really small error bars, which I haven't even put on the plot here, but they're really small. But yeah, the point is for different parameters, we are getting acceptable light curve and getting different emission hotspots. But at least we have some unique solutions. And yeah, multiple solutions are giving acceptable fits. And I want to pause here for a second. And as I mentioned, in 2021, the static field work was done. What they saw was this. So just to be clear, this is not result from the current work. This is from the static field result. I just want to make a point. So let's see. Let's unpack this slide. So we have 2 rows over here, which are showing 2 good solutions from the static work they had done. On the left side, we have X-rays from NICER telescope. And on the right side, we have gamma rays from Fermi telescope. And I think black is my data and red is my model, I mean their model. And you can see that if I just ignore the reduced chi-square value here for a second, because they have other solutions which does have good values. But that's not the point here. The point is, for 2 solutions, you see good fit of X-ray curve. When you move on to gamma rays, for same parameter set, it doesn't fit the gamma rays anymore. So what they called was something field degeneracies, which means different magnetic field configuration, that is different parameter sets, resulted in good fit for X-ray light curve. But when we moved on to multi-wavelength fitting, those degeneracies were lifted. Now, I have the work we have done so far is X-ray only for retarded field. And that's why this is an open question, but we think the answer is going to be yes, that what we are seeing here is also field degeneracy, which means if I move on to gamma ray or even radio light curve fitting later on, I might be able to say, okay, the second column is the solution, which is fitting all wavelengths and not all 4 of them. So, yeah, I mean, we are hoping, because when we move to gamma rays, it's possible that all 4 of them fit, none of them fit, or one of them fits. So we can basically say this solution is the most constraining of all. So I'm not choosing the number of hotspots. This is what my independent field configuration is giving me. Uh, these shapes actually, so for a dipolar, you will get these round hotspots, right? But if I have different subcomponents from other fields, there might be some overlap between like a round shape and an oval shape. And if you see the overlap between them, then you will find a crescent shape. So that's how we explain them physically in terms of magnetic field. But I don't decide what the shape or the number of my caps is going to be. So before making a full picture summary in the next slide, I just want to make 3 discussion points from these preliminary results. The first one, everyone can note, standard center dipole is not enough. And that's what all the literature following nicer analysis has been saying, and some even before that. So we all are happy about that now. Second one is, and I want you to think a little bit. I did mention this, but just to think about it yourself. Now I have an offset field. What's that doing basically to the magnetic field? It's generating asymmetries, right? Because if I had something centered, field line goes like this, close like this. If I have off-centered field, it's going to generate some sort of asymmetry. So my field line, which goes like this, in the other hemisphere, it's going to look like this. That's what asymmetry is for an offset field. Now, our idea to begin this centered multipolar field was to see if I have dipole, then I have an overlap of quadrupole, octupole, any component you put in. Can this generate the kind of asymmetry which is needed to explain the data? And that seems to be the case because we are seeing good fits for the centered multipolar. That's a good question. And we can't say that from just one source also, right? I mean, I can say, okay, up to third component. But the field strength value also matters there. Like if my quadrupole field strength is ridiculously small compared to dipole, we can say, okay, if we can neglect that and it's fine. But from the static field results, they have seen that the quadrupole can sometimes be 10 times higher, the field strength, as compared to dipole. So it really depends on what field configuration that's going to be. But it's important, it looks like. And then the third point is, are we seeing field degeneracies like what they saw? And as I said, we have started producing gamma ray light curves now. So that's something which is work in progress. And now coming to the full picture summary. So I did speak about why and how using NICER. And so the final what is, so we have a more realistic multipolar magnetic field. And I hope I justified that using centered field is making sense. And it's a complete description. There are no assumptions about subcomponents. We let our MCMC decide which one it wants to keep. And our ultimate aim is to, again, constrain neutron star equation of state. That's when my mass and radius are going to be free parameters. So this project is going to, in the end, is going to, what's the word? Give self-consistent values for mass and radius, which will then be independent of nicer analysis team or other results or other values which we are borrowing for now. And then we want to apply it to other nicer millisecond pulsars. We did start working on J0740. I don't know if anyone is familiar with that, but that's a binary system. So we are coming up with what changes we need to make in code for that. And if you have lost me at some point, or you're like, what this tiny human being has been rambling about, I have 3 sentences of take-home messages for you. You just listen to these and you can go home feeling like you had a productive seminar. So what we are doing is we have developed a physically founded model which implements a multipolar magnetic field. And the idea is to fit nicer data over here for millisecond pulsar and predict where the emission is coming from. And in the end, we want to populate this plot with small dots where my mass and radius for different pulsars is going to be. And then that's how we constrain the neutron star equation of state. Thank you. Right. Definitely. So I should have put a slide where I mentioned all the follow-up works which are going to be. So I mentioned the mass and radius one, putting in other pulsars. Then there is gamma ray, which we have started working on. Next step somewhere down the line is to do it for radio light curve. And for that, we do get better constraints based on the polarization results, right? So that's something which we do plan to do. It is in the proposal whenever we are submitting something regarding this project. And there are models which our team has been working on to model radio data. So it's a matter of combining everything in the end. But definitely it's multi-wavelength, not just X-ray and gamma. At some point, radio is going to be there. Mhm. Then I have what, sorry? Right, right, right. Yep, yep. No, we are not assuming that, okay, let's just overplot those things. Um, I don't know the exact details, but the code does involve the synchronization thing. So from gamma ray timing and from X-ray timing, we do see what's called the zero phase in radio. We do see where the starting point should be. If we hadn't done that, then it would have another parameter in our space, which will see where the light curve should start from to make them overlap. So it's there. Yeah.
Basic idea you have that one
Um,
have to thought
yeah.
that idea.
Yeah, I mean, it's reverse engineering in the sense because only information I have is light curve. Now, I predict where on surface that's coming from. And while predicting that, doing the ray tracing and all, I need information of mass and radius. And that's how they become free parameter. Okay, explore all the combination and give me the best one you think is going to work.
Now, one of my project has been point that they want to simulate a realistic magnetic as you are doing, realistic magnetic computing. But I asked them, are you going to structure of
The field, yeah.
but their project is something like, and so a part of the science job, the magnetic field deviates cyber and other, I think other components because of the, I mean, maybe not very
Yeah.
dominant.
Right. Yeah.
Basically, they are not going inside.
Yeah.
If they are doing that, because of the
Right.
around the thing. So how good thing telling us
Yeah, I mean, yeah.
we understand that what is the problem? Have that object has all the particles, having a particle, they interact with each other, that's equation.
Right.
And that equation of state will tell us that where the gravity and the expression will balance.
Exactly.
But if it is everything is happening on the, for example, sun. Sun doesn't have. But if I take sun, then local magnetic are because of the motion.
Yeah.
So I don't know anything about the sun basically. For that, we need solar.
Right. Yeah.
That tells us what is the emission.
Yeah. Hmm.
So I'm just making it clear that doing what you're doing, it's very important in the sense I'm having another but nonetheless, it is important. I mean, what kind of
Yeah.
how much that can tell about it. I am
Yeah, yeah. No, I understand. And I mean, yeah, I can't give a definite answer for sure. But when we are moving on to gamma ray light curve fitting, for instance, particle trajectory becomes important there. I need to have information about the magnetic field line over there to actually get the emission we are receiving. So it becomes a bit more model dependent in that sense. And that's where lifting the degeneracy between different model, between someone's approach might be might happen. Because I mean, of course, I can put some independent constraints from my work. Your postdoc can do it from their work. But in the end, we have to see what models they are using, what we are using. Has it worked for other wavelength, other sources before? So, I mean, just from one source for one wavelength, yeah, I mean, I don't want to be a smart ass and say, no, my model is the best, because of course it's not. So, yeah, I mean, it really depends on all the polar of wavelength, different sources, and then comparing it with their results and seeing like the big picture, I guess. I mean, it's a generic answer, but that's the best I could think of. I mean, if anyone else has a better answer, because it's a general question, right? So any one of you who is doing modeling or something, just think about these things at some point. That's my, I mean, he's more things than just my PhD supervisor. Uh, he was, yeah. So he's in Strasbourg Observatory. So he's, where was that? Okay.
No, you know, like I was not. I read this talking.
It's a very curious way to say it. But yeah, he was my PhD supervisor, and that's how I started whole multipolar magnetic field business. And then these people were doing static field work, and then we wanted to put the multipolar one. Thank you. Thanks for being here.